Type 1 divided by 0 into a calculator and it refuses. Some machines say undefined. Some throw an error, others flash infinity. It can feel like mathematics placed a warning sign over one inconvenient calculation and walked away. But dividing by 0 is not banned by tradition, and the problem is not merely that the answer would be very large. The real issue is sharper. Division is supposed to undo multiplication. Ask it to divide a non-zero number by 0, and no answer can pass that test. Ask 0 divided by 0, and every answer passes. One question has no solution, the other has too many. Let us build both failures, watch the graph split in two, and see why calculus approaches 0 without ever dividing by it. This is symmetry. Let's find out why. The rule becomes inevitable once we remember what division is asking. Put 12 dots on the table and divide them into 3 equal groups. Each group contains 4 dots. So 12 divided by 3 equals 4. We can read the same picture another way. How many groups of 3 fit inside 12? 4 groups. These two interpretations, group size and number of groups, meet in the same multiplication fact. 3 times 4 equals 12. Either reading can be checked by rebuilding the original 12 dots. That is the hidden contract behind every division statement. Saying a divided by b equals x means exactly that ba times x equals a. Division does not invent a new relationship. It asks multiplication to run backward. The backward test works for fractions too. 12 divided by 1/2 asks how many half-sized pieces fit inside 12. The answer is 24, because 1/2 times 24 returns 12. And 12 divided by -3 is -4, because -3 times -4 returns +12. The answers may look surprising, but multiplication checks them without ambiguity. There is exactly one result that survives the check each time. Whenever the divisor has a multiplicative inverse, division by that number means multiplying by its inverse. Divide by 5, multiply by 1/5. Divide by 1/2, multiply by 2. This is why non-zero numbers are safe. Each has one reciprocal that takes it back to 1. Now replace the divisor by 0. Suppose 1 divided by 0 equals some number x. Apply the same backward test that worked everywhere else. 0 times x must equal 1, but multiplication by 0 has a rigid construction. Take x groups containing 0 objects each. No matter how many groups you draw, the total remains 0. Negative groups, fractional groups, and gigantic groups cannot change that total. Algebra says the same thing. 0 times x is always 0, so the division asks for a number x that makes 0 equal 1. It is not difficult to find. It does not exist. Trying to force an answer does not bend one rule. It breaks every number. Let us pretend anyway. Give 1 divided by 0 a new answer and call it k. By the definition of division, 0 times k equals 1, but 0 times every number equals 0, including k. The same expression would therefore equal both 1 and 0. That alone is a contradiction. A definition that creates a contradiction cannot coexist with ordinary arithmetic. And it cannot be repaired by declaring k enormous. A billion times 0 is 0. An infinite-looking symbol times 0 is not automatically 1. Size is irrelevant because 0 multiplication erases the other factor completely. The damage spreads. Begin with 2 ordinary numbers, say 2 and 5. Multiply both by 0. 2 times 0 equals 0, and 5 times 0 equals 0, so the products are equal. If cancelling a 0 factor were allowed, we could divide both sides by 0 and conclude 2 equals 5. The same argument would prove any number equals any other number. 7 would equal -12. Every equation would become true, so equations would communicate nothing at all. A triangle could have 2 sides and 5 sides at once if we encoded the counts numerically. Cancellation is valid only for a non-zero common factor. 0 destroys the information we would need to recover the original numbers. This is why algebra contains a small phrase that matters enormously, provided the divisor is non-zero. From AB equals AC, we may cancel A and conclude B equals C only when A is not 0. If A is 0, the original equation says 0 equals 0 and tells us nothing about B and C. Multiplication by a non-zero number stretches or flips the number line without merging points, so the operation can be reversed. Each output still remembers exactly which input produced it. Multiplication by zero crushes the entire line onto one point. Once every input has been mapped to zero, no inverse operation can reconstruct which input you started with. The graph explains why infinity appears near zero, but cannot be the value at zero. Make a table for 1 divided by x. At x equals 1, the answer is 1. At 1/10th, the answer is 10. At 100th, 100. At 1,000th, 1,000. As positive x approaches zero, the reciprocal grows without bound. This is the source of the tempting answer infinity. Yet there is no final row where the denominator becomes the last positive number before zero. But every entry in the table still uses a positive non-zero divisor. The statement is about a trend. By choosing x close enough to zero from the positive side, 1 over x can exceed any finite height. It does not assign a value at x equals 0. Now approach 0 from the negative side. 1 divided by negative 1/10th is negative 10. 1 divided by negative 100th is negative 100. The values fall without bound. The right side of 0 races upward, the left side races downward. They do not meet somewhere beyond the edge of the drawing. A function cannot take two opposite values at the same input. On the graph, the two branches rise and fall beside a vertical gap called an asymptote. There is deliberately no point on the line x equals 0. Saying the right-hand limit is positive infinity and the left-hand limit is negative infinity describes the two approaches. Together, they do not produce one ordinary limit. Even if we extend the number line by adding symbols for positive and negative infinity, ordinary division rules still cannot be restored. Infinity is not a real number waiting beyond all the others. It records unbounded behavior. Expressions such as infinity minus infinity or 0 times infinity do not receive automatic values, because different processes can produce different results. In some specialized systems, mathematicians attach one point at infinity or use signed infinities for convenience, but they also restrict which arithmetic operations are allowed. No extension can keep every familiar rule and simultaneously make one divided by 0 an ordinary number. 0 divided by 0 fails for the opposite reason. It has too many possible answers. Ask 0 divided by 0 equals x and reverse the division. We require 0 times x equals 0. But now every number works. Choose x equals 1. 0 times 1 is 0. Choose 5, negative 3, or 1 million. All pass. Nothing in the equation prefers one candidate over another. For 1 divided by 0, no candidate survived. For 0 divided by 0, every candidate survives. Division is supposed to return one unique answer, so both situations are undefined, but for opposite reasons. This is why 0 over 0 is called an indeterminate form. The visible zeros do not contain enough information to determine the hidden ratio. Three functions make the ambiguity visible. First, x divided by x equals 1 for every non-zero x. So as x approaches 0, the ratio approaches 1. Second, x squared divided by x equals x away from 0, so its limit is 0. Third, 2x divided by x equals 2, so its limit is 2. At x equals 0, all three displayed fractions become 0 over 0. Yet their surrounding behavior points to three different limits: 1, 0, and 2. The symbols 0 over 0 alone cannot tell us which function produced them. A hole in a graph captures the distinction. Draw y equals x squared minus 1 divided by x minus 1. Substituting x equals 1 gives 0 over 0, so the original expression is undefined there. But factor the numerator into x minus 1 times x plus 1. For every x except 1, the common factor cancels and the graph follows, y equals x plus 1. The line approaches height 2 at the missing point. The limit is 2, even though the original value does not exist. A limit answers what happens nearby. It does not secretly perform forbidden division at the whole. Calculators and geometry use the word undefined for precise but different-looking failures. Different calculators report division by 0 differently. because their number systems have different engineering goals. A school calculator may display error. Many programming languages stop with an exception for integer division. Floating-point hardware often follows a standard that includes signed infinity and a special marker called -n, meaning not a number. It may return positive infinity for 1.0 divided by positive 0, negative infinity for division by negative 0, and nan for 0 divided by 0. Those are useful signals for computation. They do not prove that real number arithmetic has assigned ordinary answers. Geometry contains the same structure in the slope formula. Slope is rise divided by run. A line rising 3 units while running 2 has slope 3 halves. Make the run smaller while keeping the rise. The slope becomes steeper. For a vertical line, the run is exactly 0, so the formula asks for a non-zero rise divided by 0. We call the slope undefined, not because the line has no direction, but because no real slope number can encode it. Approaching vertical from the right gives large positive slopes. Approaching from the left can give large negative slopes, echoing the 2 branches of 1 over x. Units offer another warning. Speed is distance divided by time. 100 meters in 10 seconds is 10 meters per second. Shrink the measured interval to 1 second and the average rate can grow. But 100 meters in exactly 0 seconds is not an ordinary speed measurement. It asks for a finite change across no elapsed interval. Physics replaces that impossible quotient with an instantaneous rate defined as a limit of smaller and smaller non-zero time intervals. Again, the useful answer comes from nearby divisions, never from setting the denominator itself to 0. The correct response is not to ignore 0, but to ask a better nearby question. When substitution creates 0 in a denominator, calculus pauses before declaring anything. First ask whether the numerator is non-zero. If so, the expression may grow without bound or split into opposite one-sided behaviors, as 1 over x does. If the numerator also tends to 0, simplify the structure, factor, rationalize, or compare how quickly both parts vanish. Different hidden rates can create entirely different limiting answers. Only then take the limit. This decision tree separates 3 ideas people often blend together: an undefined value, an infinite trend, and a finite limit through a removable hole. Here is the whole rule in multiplication language. For a divided by 0, search for x such that 0 times x equals a. If a is non-zero, there is no such x. If a is 0, every x works, so there is no unique choice. That single test explains both failures without memorizing separate prohibitions. It also tells us why every non-zero divisor behaves differently. Multiplication by, it keeps inputs distinct and has exactly 1 inverse. 0 is unique because it collapses every possible input onto the same output. Return to the calculator button. 1 divided by 0 is undefined because multiplication cannot undo it. 0 divided by 0 is indeterminate because multiplication cannot choose among its endless candidates. Infinity describes how some nearby quotients behave, not a value that repairs the broken inverse. And limits let mathematics study those nearby quotients with precision while leaving the forbidden point empty. Division by 0 is not a mysterious exception pasted onto arithmetic. It is the exact boundary where multiplication loses all information, and an inverse operation has nothing left to recover. You cannot divide by 0 because division must reverse multiplication, and multiplying by 0 erases the number you would need to recover. Thank you for watching Symmetry, where math, physics, and chemistry are explained deeply, not dumbed down. Subscribe for the next construction.